Hello, welcome to the third part of our series on working with Azure Databricks. Up to now, we've covered ingesting your data with Data Lake, as well as exploring your data with Databricks SQL. And today we're going to really get to the payoff where we're going to show you how to map out the data and insights that you have in various ways. And we'll lead it off with Nikhil Gupta from Databricks. Over to you, Nikhil.
Hey, good afternoon, good morning, guys. Let me go and quickly show the presentation. So we are good. So welcome to the part 3 of the Microsoft Azure Databricks radio series. I am Nikhil Gupta. I work as a senior solutions architect. Along with me, we have John O'Dwyer, and he would be I'll let John introduce in a bit. So he's a developer's advocate at Databricks as well. So the idea for today, for the last part 2 series, we have been looking at how to ingest the data. We use the weather data. And then, the part 2 of the series, we looked into how did we use Databricks SQL to perform SQL analytics on top of the data. Today, the part 3 of the series, what we're going to look at is how to create a machine learning model using the same data set and then, get some insights out of that. So my presentation today would be revolving around how to do data science and machine learning onto the Databricks platform. So as we look today, the ecosystem, we have a lot of libraries, a lot of software that's available to create those models, right? We have TensorFlow, Scikit-learn, Keras, a lot of libraries available where you can give the data set to it and you can get a model which can do predictions on those data set. But if you look closely, right, the entire machine learning lifecycle, taking a model right from your desktop to the production environment involves a lot of steps. And actually, if you look at it, the code that is really used to generate the machine learning model is actually a very small part of the entire machine learning and data science projects, right? It includes things like feature extraction, data collection, data cleaning, and then on the other side, you have to put that model, serve it out in real time, monitor the results, and so on, so forth, and so forth. And that's what the value proposition of Databricks comes in. We are on Databricks, you can do end-to-end machine learning onto a single platform. So what we did, we took all those features, right, which we talked about, we packaged them, and then we created something called a Databricks machine learning environment. So as a unified platform, data scientists can go into the Databricks machine learning environment and do all those all the activities, end-to-end activities, right? So the machine learning environment basically consists of your data science workspace, and we'll go into one by one into all these components. We'll talk about AutoML, and really I want to really focus on the ML ops, the ML flow, where you can take the model, you can monitor, train it, use model registry to get the best run out of it, and finally go it and serve it in the real time, right? The thing which we covered earlier was more, and I'm not going to cover in this one, is around Delta Lake and ADLS, right? So we assume that, data is already present in Azure Data Lake Services, ADLS, and has been converted into a Delta Lake format. So let's go in and learn about the data science workspace. What are the main components of the data science workspace that we have? So the first thing is the notebooks. Databricks notebooks provide a collaborative environment where data scientists can come in and create those machine learning models. Databricks notebooks is a multi-language, it supports multiple languages. So you can use Scala, SQL, Python, R, all in a single notebook. The second important thing is visualizations. So data scientists basically needs to do a lot of visualization on the data. They want to things like finding outliers, finding skew in the data. So Databricks notebooks provide those built-in visualizations where you, with a few clicks of a button, you can create those charts out of it. On top of that, we support a lot of popular libraries. You can bring libraries like matplotlib in Python or ggplot in R and create those visualizations which you can look and explore data further. The other component around Databricks notebooks is reproducibility. So each time you go in and make a change to the notebook, it is auto-logged with the revision history in place. Further, if you want to integrate those notebooks with Git or Azure DevOps repos, you can definitely go in and link those notebooks to your repositories. The notebooks are collaborative in nature, so multiple data scientists can work on a single notebook in real time. They can co-edit the notebook and leave some comments around it to make it much more easy and usable. And finally, all the notebooks are enterprise ready. So enterprise securities, auditability, all things are present in here. So once with the notebooks, the next thing is around compute. So compute in Databricks is governed by something called clusters. So with a few clicks of a button, you can configure a cluster which can take in your code and run in an optimized fashion. So with clusters, think of clusters as you get a bunch of VMs from Azure, and then on top of that, we install our runtimes, the software, and then whatever commands you're writing, you can run on those clusters. So a few features I want to mention about the clusters, right? So the first is it's compatible, and we support almost all VM types on Azure. It's optimized, gives an optimized performance, Spark performance. We realize, some of the machine learning models would require GPU support. So we do support GPU enabled clusters as well. And finally, the clusters are pretty elastic. You can auto scale these clusters, which basically leads to, cost optimization. So very hassle-free, you can create a very hassle-free compute infrastructure, put your code in your notebooks, and then, go and run on those clusters. The next thing is about Databricks runtime. This is also a really important component. So runtime, think of runtime as a software, the Databricks proprietary software, which is installed on top of the clusters. So with the runtime, you get a machine learning or an ML runtime, and this runtime is basically optimized to run machine learning workloads. So some of the cool features are like the most libraries come pre-packaged, say TensorFlow or your XGBoost, scikit-learn. They are already pre-installed and optimized to run on those clusters. Further, if you want to do your training models in a distributed fashion, you can definitely use some of our libraries to scale those trainings onto hundreds of machines. And finally, the runtime, the machine learning runtime comes with ML flow and AutoML built in. And we'll talk about ML flow and AutoML in a bit. But these all come built in with the machine learning runtime. So we talked about the data science workspace. The next thing I want to talk about, how does the end-to-end flow looks like using ML flow and data prep and scoring and model scoring as well. So this is the big picture end-to-end on Azure, and let's look at one by one each and every component. So the first part is your ETL. So you have your data sources. Data could be coming from a batch source, from a stream source. You would use Azure services like ADF and Azure IoT or Event Hub to bring in all sorts of data onto the Azure ADLS. or your data lake, right? And that would be raw events. And then you would use a Databricks notebooks and clusters to convert those raw data into the processed data form, right? You could use a medallion architecture, say from bronze, silver, gold. And once you have the processed events, right, you can start creating those models or start working and doing data science projects onto your data. And this is how the data science infrastructure would typically look like onto your platform. So now we have the processed data inside my ADLS. I would start creating those models using my libraries and ML runtimes and notebooks, and start creating those using those TensorFlow and XGBoost to create those models, right? As we talked earlier, you always have the option to link those notebooks to your Azure DevOps repos and create those CI/CD pipelines. So once you have your models all done, let's assume you have a model all done, you go and train that model. So you go and say do hyperparameter training, tune the parameters, and you make say 100 runs on that model, right? So each time you make a run, that run would be stored in something called a tracking server, right? So you can track how many runs I made, what parameters got changed, and how does the result looks like. So you can track your runs in something called a tracking server. Tracking server enables you to store parameters, to store artifacts, and even store models within the tracking server. So once you've made all those runs in, the next step we will go around is select the best model. So out of my 100 runs, I find my perfect run, which I believe would go in and give the best runs in real time. So I go in and select my best model and then move it to the model registry. So think of model registry as a place where you go in and tag your run and say, okay, this is my run, and I want to go in and move it to the next stage. So I go in, I tag my runs, and then finally, once I'm here, I move to the next step, and which is my ML ops. So I take my best model, I move it to Azure into say something like Azure Container Registry or Azure Kubernetes Services, and I move the model here. And now my model is ready to be served in real time. So I would get a REST API URL, which I can give it to the user. The user can hit it from data and get some inference out of it. So this is how a typical end-to-end machine learning life cycle or project would look like in terms of taking your right from data ingestion to model serving on Azure. So we talked about this earlier, just brief overview of how things work, right? You create those models, you put them in the tracking server, with all the runs. And finally, once you're ready with your runs, you move it to model registry, and then you can go in and serve it out. So we have, you can serve it out on Databricks REST endpoint, or you have tons of options where you can, go. And some of the most popular serving infrastructure is on Azure Machine Learning. And the last part I just want to talk about is AutoML. So this is a new feature that came up during the Data and AI Summit this June. And I just want to quickly talk about what does AutoML do on Databricks. So AutoML on Databricks basically is a glass box approach to machine learning. It helps you to automatically apply machine learning to a data set. So all you have to do is you have to provide it with a data set, right? And once you have your data set and you say, okay, this is my data set, it will go in and automatically do the data prep for you. It will do feature engineering. It will automatically run. It will do multiple runs on that data set, find the best model, and then it will give out some of the results, and and then it will give out the output. So what does the output looks like on AutoML? So first is, AutoML integrates smoothly with existing ML flow tracking server, automatically creating an experiment listing all the models created by AutoML. So if you see over here, it will run experiments, it will run models like logistic regression, decision, random forest. All those models would be constantly run on that data set. And then finally, what you would get is a set of notebooks which each model run, right? You would also get a data exploration notebook, which basically gives you summary statistics, which gives you the data exploration results. And data scientists can take this and if they want to do some more, these are it's a bunch of notebooks. They can go in and develop further on those notebooks, right? And then finally is the trial notebooks. So basically for each potential model that is trained, AutoML will generate a notebook which can reproduce that model training. So the key here is, why we call it glass box is basically, you quickly get the code written in the notebook. And now data scientists, data engineers can go in, data engineers can go and create more features on top of it. Data scientists can go in and do a much more hyperparameter tuning and change those parameters. So what are some of the features available right now? We are able to do problem types, classification, and regression. Time series would be coming soon. The main models which we run on a scikit-learn, XGBoost, and HyperOpt. The support for TensorFlow would be coming soon as well. Features is numerical, categorical, and timestamp. It's fully integrated with MLflow. Evaluation is done via SHAP and MLflow as well. And then you can go in and deploy using Databricks model deployment and do batch scoring on top of that. So that's a brief, quick overview of how to do machine learning onto Databricks. Now I would pass it to John, who would help us and see the demo around the weather data set.
Thank you, Nikhil. Let me share my screen. Sorry, it's asking for 1 second. Okay, let me see if I can do this one more time. All right. Okay, hopefully everybody can see my screen. And we are, I just wanted to give a little bit of background before jumping into our notebook. Just to remind everyone that this is actually the home screen that you land on when you come into a Databricks workspace. Nikhil also mentioned compute. We have a cluster up and running right now called Dev, but to spin one up whenever you need it, you just have to give it a name and you're pretty much off to the running. The versions that we're actually going to use here are 8.3, based off of some limitations at the moment. But this is pretty much standard, and we can create the cluster and just get going. So after we've created a cluster, we can go into our notebook and start to work. In this notebook, based off of the 2 data sets that we have at the moment, one being historical weather data and also taxi trips in New York City, we're going to pose a question. And this would be a question as a data scientist in the past, these would be questions that you would be asked. And the question that we're going to ask here is, does weather affect taxi trips? If that's the question that we're posing, you know, where do we even start? Well, you start with the data, and as Nikhil pointed out earlier, the piece that's really ML code is a very small piece of the whole process. And what we're going to do here is we're going to actually go through and kind of think through this problem and use various tools in Databricks to solve this problem, or to answer this question, excuse me. And what we have is, first of all, we're going to install our libraries. In this case, we actually need to install Azure ML open data sets. What we use that for is to grab the NOAA data. These are just a couple of the configurations and libraries that we're going to use. So first thing that we do, we're going to pick a set of NOAA data to pull in. We're picking this set of data based off of essentially what we know that we have from our taxi data that can be used. Well, after pulling this in, we're going to look at this information. We have a massive amount of information. We're only showing the first 1,000 rows, but this is every reading of every NOAA weather station essentially around the world between 2016 and 2019. It's a massive amount of information. And where do we even start? You know, one, we can actually start by saying, okay, we know that we're in the US and what the station is. There's also lat long here, but that's, you know, that's really needles and haystacks. So what I decided to do to determine which weather stations and which sets of data to even use was, well, we have this nifty feature around mapping that we have in Databricks SQL. And so what we're doing is, I said, all right, well, let's break this down to station and lat long associated to those stations, and set up that data in a table so that we can see it in Databricks SQL. And that's exactly what we did. I just ran a very simple select statement off of the weather stations that we aggregated here. And it looks like let's start by just drilling into America. And I'll make this a little bit bigger. So this is essentially off of the query. All I did was make a map marker set off of the query, and we're just drilling into New York City. So what we can do here is now what we see is we actually have this is Long Island and Manhattan, and this is the Manhattan Island, and this is Long Island here. If you know the city at all, what it looks like is we have some places in LaGuardia. And what I'm going to do is assume that the New York City taxi weather would probably be very close to what we would see in LaGuardia Airport. And it looks like these are both LaGuardia Airport station names. They probably just moved from one side to the other at one point. Maybe there was a tower that was taken down and moved. But essentially what we're going to do is we're going to use the station of LaGuardia Airport, and instead of trying to do this programmatically, sometimes it's just easier to understand information by looking at it and really drilling in. And that's actually to Nikhil's point about looking at data and understanding what's there. Because we do need to, one, pick a good location to look at the data, the sets that are associated. We could have picked something here in Manhattan as well. And after picking LaGuardia, what we did was I first, on a daily basis, for all of the stations, I wasn't sure which ones we were going to use. We summed the rain and the snow. There were both. There was a there was a value that was associated on an hourly basis, and I took the max and also the sum. And we're going to use the sum values of these. I'm going to actually mix them together to make an accumulation value, as opposed to rain and snow separate. But that's what we're doing. We're then going to limit the data that we look at to the station of LaGuardia, so that we can really drill down this as a feature set. So what we're now doing is we're taking the weather data and all of it, and we're now framing the question around ML. And what this is doing is we say, all right, well, of all of this information, which is the needle that we need? Well, the needle that we need is LaGuardia station information. And in there, we're going to look at the summation of the rain and the snow on a daily basis, the accumulation, and that's actually going to be the feature. Features in ML are, in an ML model, are the factors that you use to do a prediction. And what we have here are, this first feature that we're building is a daily amount of rain and snow. For every day that we're going to look at what New York City taxi trips look like. So coming down to the next data set that we're going to look at, that we've discussed in the past as well, is this New York City data sets. And if we look at it, we actually we have this data locally. If you have a workstation available to you, or a workspace available to you now, you can go in and find this this data. It's a Databricks dataset, New York City trip data. We're going to actually look specifically at the green taxi data. So we, and this is something that we've done in the past as well, we've actually gone in and pulled this information. If you like, you can also pull this information from the Azure ML data sets that exist there as well. And we'll display the values just like we did for our station data. This usually makes sure it gives you a little bit of a sanity check of what you're looking at. It also gives you the ability to start to look at the values that you want to break down into features on a daily basis. So as we see here, we're at the date time level for every single trip that a person made in a green taxi across all of history. It actually starts back in 2015 and it goes through 2019. So this is every one of them, and we're going to start looking at these different values. We're actually going to start to focus on fare amount and I believe total amount actually. So when we start to think through, okay, what do we really need? Well, one, we need to aggregate this information on a daily basis. And to do that, we're going to pull the date time, and we're going to actually make a date associated to it, and we're going to do it off of the pickup. Then we're going to break down those values and correlate them to what we're getting out of the NOAA data, so that we're going to pull from the middle of 2016 to the end of 2019. And this is essentially how we're going to break that information down. We are aggregating these values. We're getting both summed values for distance, total fare amount, and we're also going to do a trip count value as well. We're going to really focus on the fare amount though in here. Just seems like the right value, quite frankly, that would be associated if we really think about it. You know, you could probably look at trip count. If it's raining or snowing, you're probably going to have a higher trip count. You're going to probably have higher distances, but at the same time, like, you know, the actual overall dollar amount is probably what people really care about. So we're going to focus on that one in this in this case. But you're welcome to actually take this and augment it in the way that you want to, so that you can see it in different ways. So we're going to write that data out as a Delta table, just like we did for the daily weather data for LaGuardia as well. Just kind of do a sanity check on the displays data here, so that we can do the same type of just little analysis. We're going to write it out as a table so that we can then see it in SQL. And I'm going to actually show you what that looks like. So if we look at this data, we look at starting in 2016, going through 2019, this is what the total fare amounts look like. The correlation for distance and trip count is very close. They are all in decline. I think we can all agree that this decline is probably directly related to ride sharing and potentially, you know, like, one of the reasons I wanted to look at this is one, to do the sanity check on the data itself. It does look like there is some inconsistencies in this data that we could potentially pull out if we want. We're going to let them be, but then on top of that, it also does show that trend of essentially yearly decline. So we're going to bring that yearly decline up in later, but it is something you just want to look at it and get a sanity check so that you just, before you plug this this information into models, you kind of have to have a decent idea of what things look like, so that you can make sure that, you know, what you're looking at in a model, are you seeing erroneous results because you have bad data? Think of the old adage, garbage in, garbage out. We're just kind of doing a sanity check on that. But at the same time, we are cognizant that there is a decline in taxi data over the course of time as well. So coming back to our notebook, what we're doing here is, now that we have both of these data sets, we have to combine them together. So to combine them together, we're going to do that we're going to do this as a join on the date. And we're going to call this the daily feature set. So again, ML features are the values that you use to predict something. And in this case, we're calling it daily features. We're going to drop the extra date column here. Then we're also going to give a day of week feature associated to the day of week. It actually comes out to be an integer, 1 through 7, so that we can correlate what those values are, you know, based off of, was it a Monday morning or was it a Saturday night? I'm assuming that there's going to be many more people taking cabs in New York City and on a Saturday night, but then there is on a Monday, and it can probably indicate that that is the case, or maybe it doesn't have effect on it. But it is another feature that we can use to understand what does drive these types of predictions. So we'll write those values out as well so that we can pick it up if we wanted to. So to answer this question, does weather affect taxi trips? What we're going to use, we're actually going to build a model, and then to determine if there is a correlation between weather and these trips, what we're going to do is we're actually going to build the model. We're not actually going to use it for prediction. We're going to use it to pull out something called the feature importance that's associated to these models. So keep in mind, ML usually is used for prediction. In this case, we are actually building a model that could do prediction, but at the same time, the question is really does weather, or in this case, does accumulation, rain or snow, make a difference when you're at to fairs in New York City? The theory is that it does, but we're going to look into if that's the case, and to extract that information. What we're doing is we're building up feature sets that are associated to this information. The features that we will pull in, and I'll show you in a second, are going to be day of week. We're going to pull in month and day, and an aggregate of some rain and some snow. And our product our value that we're actually going to look for is the sum total fare. So taking those values into account, this is the set that we're actually using. So first of all, I did want to point out one thing. We are not going to use year in this case. As we determined from our graph, on a year-by-year basis, it's definitely in strong decline that we can visibly see based off of that, based off of the decline in fares over the course of time. So what we're going to actually do is we're going to leave out year, because we could actually put it back in, and you can see this, that year is actually the predominant factor in this case, so much so that it pretty much, because of that decline, it's gonna basically kind of water down everything else, and we want to take it out to actually see if the accumulation of snow and rain does still have an effect even without it. So our numeric columns are going to be month, day, and the sum of the rain and snow. I wanted to point out we're using something called gradient boosting trees, or GBT. And for those that don't use ML a lot, don't be scared of this. These are practical things that you can use. A gradient boosting tree algorithm essentially makes it makes multiple versions or multiple trees of a prediction, and then it uses each one of those to actually get to a good answer. So it actually, and then there's another variation on this called random forest, also available in Spark ML, which is what we're using here. And these tree-based predictions, essentially, we're using them so that they can then be used for recall, so that they're not overfitted, but there are multiple versions, and then it basically coalesces into an answer. What these tree-based models allow us to do. It actually is it is one of the reasons that these are so popular, is that you can actually determine if a feature is more or less important than others. This is very hard to do in the case of deep learning, but it's actually pretty easy in the case of tree-based modeling. Something else for those who aren't too used to doing ML, there are generally two different types of answers that we're looking for, and or labels actually is the correct term for that. But we're either going to look for numbers, or we're looking for a classification, and classification being true, false, red, blue, cat, dog, whatever it is. And when you're looking for trying to predict a number, that is regression. And if you're looking for a categorization, that is a classification. So we're doing regressors because we're actually trying to predict what the dollar value is for a daily set of rides when it rains. So these numeric values, like I said, are month, day, and the sum of the set. Even though day of week is a numeric integer in our case, it's actually a classifier. The reason being is that it's not necessarily, you're not looking for a value between 1 and 2, because if 1 is Monday, 1.5 is not Tuesday. You're actually looking for the category there, and we treat in the case of Spark ML, we treat that as a string indexer, and then it breaks. What this is going to do is it's going to take that and it's going to actually turn it into a category, and use it as a column associated. Now, what we're going to do is the indexer actually takes the day of week and it turns it into a day of week index. And the feature columns that we're actually going to pass in here are going to be those numeric columns plus this extra special one. We then package that up into a set of columns that we put into one column called features. We then tell the model, hey, we want it to be a gradient boosting tree regression analysis model, and here is the set of features. It's in our column features, and our label column is called sum total fair, and that's the label being the value that we want to try to predict. So we put all of this together into a ML pipeline, including imputed values if you need it. Apologies for not pointing that out. That essentially will put values in if they don't exist. Then we are getting the day of week indexer so that we get that indexed value. We then package them all together into a vector and then run our model. So what we're doing here, generally speaking, we would usually have a test train set that we keep separate so that you can train a model against the training set and then test it against the set for prediction after the fact. In our case, we're not necessarily really looking for a prediction, so we're actually going to do it on the full feature set, and so that we can actually go and look at the feature importance that exists here. So to answer the question, do we think that rain and snow is important? We're going to take this fitted model, and we're going to look at the output of the feature importance associated with each one of our features. In this case, we take the feature importance of the gradient boosting tree model. We then we're going to make a little pandas data frame where we actually take those values as an array, and we add the feature columns associated to them, and then we're gonna name them as well, because these the first three are not associated. But in the end, what we see is that the feature importance is actually the second highest feature importance is associated to the accumulation for a day, whether it be rain or snow. And if we actually look at the other values, so this is the second most important feature. The other being month, which makes sense to me. Actually, you know, people are probably less likely to take a taxi on a beautiful spring day as they would in the middle of the winter, I would imagine. And day of week actually makes sense to me as well. This value here, the day, it does look like we had a couple weird values that came through. If we wanted to kind of drill into this a little bit further, we would probably try to impute those anomalies and actually smooth out the values associated over the course of time, because this seems like this might be a problem that's still incorporated in that data set, but that's just thought. But this is an example of how you can take these two different data sets, or really any two different data sets, because usually what you're trying to do with data science modeling is really you're answering questions, and you're almost as like you're a data alchemist, where you're trying to say, all right, well, how do I solve this problem? Or the other way is to say, all right, if I have these different data sets, how can I potentially put them together to find intelligence in them and use them for prediction, or to understand, in this case, if weather does affect how much people pay on taxis on a daily basis. So that's what we have for the day. We actually also have a special guest here, David Sanchez, that's actually going to talk about other parts of this around what we did was we showed a lot of stuff around mapping, and we really wanted to also bring in a specialist on Azure mapping specifically, and David is a Azure mapping specialist, and we brought him in to actually discuss how we could do small pieces of this as through Azure mapping, or Azure Maps. Over to you, David.
All right, awesome. Hello, everyone. My name is David Sanchez. I'm a program manager in the Azure Maps team. And since this session, we had a lot of map data and weather services, we wanted to cover basically what is Azure Maps. Azure Maps is a set of geospatial APIs that developers can start using to include location intelligence in your applications. Many applications, or almost all applications, need location capabilities for basically an address form, or even like more advanced features, like, for example, in this case, data analytics. Basically, Azure Maps, it's built on top of the world-class partners like TomTom and AccuWeather. To talk about the different capabilities of Azure Maps, Azure Maps is a native service, meaning that basically it's complying with all the Azure services that we have. It provides an Android and iOS SDK, along with the web SDK. Basically, it's in the standard with the Open Geospatial Consortium standards. It also provides flexible pricing. Like any other Azure service, you pay for what you consume. And yeah, it's basically supported in the government cloud as well. And it integrates with other Azure services. To talk about the different features that developers can start using from Azure Maps. First, we have the map rendering, maps controls, map visualization. We have the SDKs that we mentioned. We have the mobile SDKs and we have the web SDKs. We have routing search capabilities from multiple points, even waypoint optimization. We also have the spatial operations. Like for example, if you need to create a U fence and you need to get like alerts or notifications, you can start doing solutions like that with Azure Maps. We have traffic as well. Traffic is updated every minute, and it includes incident details. We have time zones. We have geolocation to get the location of a specific API. IP. And we have the weather service. This includes basically the current weather conditions and also a forecast up to 45 days with alerts. We have the data storage for Azure Maps Creator. Azure Maps Creator is basically an indoor mapping solution, meaning that you can bring your private map data with your CAD files for doing indoor mapping. We have the government cloud support. Azure Maps integrate with Power BI for visualize basically geographic data. And we have the elevation service that is basically supporting any part in the globe. So in terms of samples and basically the different features that you can get, you can go to this website, the Azure Maps code samples. I'm putting that in the chat. From here, you can explore the different features and the different capabilities that we have. You can look for weather. And from here, you can see, like, for example, we have show weather overlays on the map. Something important is that you can create map visualization and you can add multiple layers of the data that you have, including like multiple data source. So if you want to use a solution like the one that you just saw in the demo that John did, basically you can use that as a data source on the maps control, or you can use basically the Azure Maps Weather Service API. You can get basically weather conditions or weather alerts along the route or basically any part on the map. We also have like, for example, traffic. As I said, this is basically updated every minute. And you can see in this case, basically, this is an example in New York. This is how it is right now. If you would like to implement a solution like this, all these samples are basically open source. So you can find those in GitHub. You can come here and basically see how the different solution is structured. Like, for example, in this case, we have the initialization of the map. We have the authentication. In this case, we are using Azure Active Directory, but you can also use the subscription key. And then you can take a look at basically how this solution works and how the traffic API is called with the map control that we have. The other basically demo that I wanted to show is the Azure Maps Creator. This is for indoor mapping solution. So if I zoom out, basically this is like any other map that you have. But as soon as I zoom in, I will basically take a look at the building. This is my private map data. This is only available in my tenant. And this solution is integrated with Microsoft Graph. So I can see the people that are assigned to these offices. As you can see here, we also have this one. You can also see, like, for example, the routing. So in this case, I get the how to get to this office from the lobby. This is basically good for see the conference rooms that are available. I can book these rooms because this is basically, or see which ones are reserved because this is connected to the Microsoft Graph API. I can navigate through the different floors that I have in the building and so on. I can set up alerts, customize the styling, and this is basically another service of the Azure Maps. With that, basically, I just wanted to cover a quick overview and making sure that for those that are not familiar with Azure Maps, I invite you to take a look and see these solutions. Thank you very much.
Cool. Thank you so much, David. I'm just waiting for my controls to get caught up so I can get myself on camera here.
We can see you.
Okay. So thanks to everyone who tuned in for this series. We've got the materials up on GitHub. We'll have the recordings available on our YouTube channel tomorrow. And if you have any questions afterwards and you want to get in touch with us, I'll go ahead and put this email address in the chat. You can reach out to us at msusdev@microsoft.com. And huge thanks to our friends at Databricks for delivering this series. Really interesting stuff, very powerful. And you moved us through a lot of information really efficiently. So thanks, everybody. Sign off.
I will say all that information is in the GitHub repo if you want to go back and do it yourself. So keep that in mind.
Yep, and if you get stuck, send us a question. We'll get you in touch and we'll get answers. Thanks so much.
Thanks.
Thanks, guys.